Hello everyone, welcome to a new video series Practical LLMs. Me and Raviteja have recently started an independent open source initiative, Telugu LLM Labs. We want to share our exploration of building Indic LLMs, so specifically sharing datasets, models, training code, tutorials, etc. You can find more details on our Hugging Face page, Telugu LLM Labs. One of the biggest issues with any new open models, be it Llama, Gemma, Mistral, is understanding the model performance for Indic languages, example Hindi, Telugu, Tamil, etc. So in this first tutorial, we'll take a look at Google's Gemma tokenizer that has a 256K vocabulary size. Gemma is one of the best models for Indic text generation, given its large tokenizer vocabulary size, as well as the fact that it is trained on 6 trillion tokens. We will understand how to check coverage for a particular language in the model's tokenizer and also look at the vocabulary of the tokenizer in general to understand tokenizer in detail. Let's get started. Welcome back. So you can look at Telugu LLM Labs here, where you can go to the Hugging Face page where we have collections, models, and datasets that we have released so far. Now let's come back to the tokenizer code. Let's first install Hugging Face Transformers library. Once the Hugging Face Transformers library is installed, let's run the code to get the Google's Gemma tokenizer. So here we are using Google Gemma 7b, and these are the 4 files that are downloaded from the tokenizer. Essentially, if you go to models and type Google Gemma, you can see under files and revisions the corresponding files for tokenizer, config, and tokenizer JSON. These two files are small, special tokens map.json. You can look at them. Very simple. Special tokens, beginning of sequence, end of sequence, pad, and unknown. So nothing too complex here. Then we have tokenizer config.json. It's also simple, where you have some details about the added tokens, pad, end of sequence, beginning of sequence, etc. The biggest file and the most important file for us is tokenizer.json. Tokenizer.model is a binary file. If you want, you can use Python bindings to even look into that. But for most of our use case, if you look at tokenizer.json, just download it and look at it with your editor. We are going to just see that in a bit, but let's get back to the code. So tokenizer has these 4 main files, out of which I would say, if you want to understand the several tokens present, etc., tokenizer.json is most human readable, and you can look into that. But before that, let's just print the we get the vocabulary and print the total number of tokens that are there in our Gemma model. So this is the code to print, and as I've mentioned it before, Google's Gemma has 256,000 tokens. Let's look a little bit deeper into the tokenizer. Let's print the first 500 tokens and the last 500 tokens from the tokenizer. Here I've written the code to just sort the tokenizer by the second key value, essentially the ID value. In order to understand, let's just look at the tokenizer.json file quickly. So essentially it has these things: version, truncation, padding, some added tokens, and just some special tokens, etc. And the most important part for us is model type is byte pair encoding, and here's where the vocab starts. So pad is 0 and end of sequence is 1, beginning of sequence is 2. So the token and its corresponding token ID. So if you scroll down, you can see that there are some unused ones, and from 108 to 138 it's just new lines. So if you get a combination of, let's say, 15 new lines, you would assign it a token of 138. Similarly, again, underscore, then a few HTML tags that you can see. So this full table tag will be assigned one token, and that token is 169. So similarly, you have some hex code here, and then starts this. And if you scroll down further, you can even go to the part of 256k, where you have these Chinese characters, etc. And similarly, we have all the characters. And now once the tokenizer 256k are done, then you get to merges. Merges is another key where, if you see ANN, then OTA, TION, it will be merged into one. So this is for sentence piece model, where the merges that needs to happen are also stored in the file. But anyways, let's get back. Now you understood that there is a token and corresponding token ID. So we are sorting by the token ID just so that we are in ascending order, and we are printing the first 500 tokens here. Let's look at that. So the same thing that you have seen in the file that I've shown you. You have the pad token, that is 0, end of sequence, beginning of sequence, unknown, mask, and there are a lot of unused tokens till 108. And this might look a little weird to you, but as I mentioned, this is basically \n. So a sequence of 15 or 20 \n current sequentially ascending. So for example, token 136 would be like 18 \n's, etc. Similarly, you saw these tokens, and then you have most popular HTML tags as tokens, then the bytes, individual bytes as tokens. Then slowly it will start getting with English language tokens, etc. Similarly, let's print the last 500 tokens. So if you see the last 500 tokens, again some special characters, some Chinese, Japanese characters, etc. And again a long sequence of space, etc., spacebar, etc. Then you have a start of image tag, something. So at the end of the day, your Indic languages token, be it Telugu, Hindi, English, would be one of these. Telugu, Hindi, Tamil would be one of these 256k tokens. But how do we get to that? That's what we are going to see next. First, let's look at Telugu Unicode block. So you can actually go to this Wikipedia page for Telugu Unicode block and read about it. At the end of the day, technically all the Telugu characters fall in this Unicode range. So C00 to C7F. So from here to here is where all the Telugu characters fall into. And similarly, you can look at Devanagari, which comprises of Hindi, Marathi, Maithili, Sindhi combined. Then you have Bengali Unicode, Gujarati Unicode, Oriya, Tamil Unicode, Kannada and Malayalam Unicodes as well. So simply, if any of the characters in our tokens comprise of these Unicode characters that fall in this block, then we are going to filter them and their corresponding IDs. So let's run this code and it will be very evident for you. So here I am picking the start C00, that is this C00, basically this. and ending at C7F, that is this column. So this full range from C00 to C7F is what I'm taking for the block, Telugu Unicode character block. And I'm iterating through all the vocabulary items, and ORD gets you the Unicode range to compare. So you can iterate through each of the token, so each of the character in the token, and if it falls in this range, you are going to filter that as Telugu tokens, both, and store both the token as well as the token ID. Now this part is essentially kind of redundant, but I added it for extra safety. In case the character doesn't resolve well, you can even go deeper into the character, then you can do Unicode data and see if that contains Telugu as well. But technically you can kind of consider this probably not essential. This code itself is sufficient. But at the end of the day, once you get Telugu tokens, you get the length, and you basically print each of the token and token ID. And let's see how it looks. So essentially, if any character in the token contains a Telugu token that falls in this Unicode range, we are going to filter that. So technically speaking, you might even have Telugu combined with some other word or letter, etc. But it's very rare to have a mixed token, since already the percentage is very less. So at the end of the day, you can see that these are all the Telugu tokens that are present. And how many are they? The total number of tokens with Telugu characters is 233, where the total number of tokens is 256k. So essentially, the percentage of Telugu tokens in the vocabulary is 0.09%, very less. But the thing to remember is that even if you just have coverage for individual letters, which we do have, since it is trained on 6 trillion data points, at the end of the day, a tokenizer is just a lookup table where it is going to return an array of fixed length from the model. So the tokens are initialized at random, and after all the training of the 6 trillion tokens that has, let's say, large percentage English, Telugu, of English and little bit of Telugu, etc. Still the tokens after training do carry significant value. The tokenizer array is trained and it is of high quality. So even if you have individual character tokens, for example, here it is A is just right here. So even if individual characters are covered and they are very well trained tokens, still it is pretty good. It is much better than expanding the Llama 2 tokenizer, expanding the vocabulary and training from scratch, because you need huge amount of data to even get to high quality vector for each token if you're training from scratch, because you are initializing just normalized values or random values. Now let's see what this Unicode data is doing if you want to understand. At the end of the day, if you just give A, it's going to resolve to the name of it, which is Latin capital letter A. I'm going to give E here as Telugu character and C. E is basically this, UC07. Let's run this and it will resolve to Telugu character E or I. Now I want you to understand one thing, why we have iterated through character in token. For example, if you're just speaking English, you would understand that this might be a single letter. For example, in English, this might just be A, B, C, D, E, F, G, H, 1. So if you just do for character in this, you are expecting it to just print only one letter, let's say A or something like that, because it doesn't look like a word to you. but I want you to understand how the Telugu characters are. For example, this, although it looks like one single letter, it is not one single letter. It is a full grapheme, basically Stri, which means woman, pronounced as Stri, and you'll understand it once I just iterate through this simple looking token. So basically it is comprised of Sa, Virama, The, then Virama, R, and vowel sign. So vowel sign E. So basically it's like Sa-three. So Stri is composed of these 6 individual Unicode letters from here. So for example, Sa is here, the first one, then R is let me see, yeah, R is here, so Sa, R, and then Ta is somewhere here, Ta. So similarly you can see that basically, although for if you're not from Indic language speaking community, this might look like one single letter to you, but at the end of the day, I'm telling you that if you just iterate through in Python, you are going to, and you just print the characters and their corresponding Unicode names, you will see that it's comprised of 6 different Unicode characters from here. So I just want you to understand that, so now we are checking, so we are iterating through the complete characters in the token, and again, and checking both if any of the Unicode names or any of the Unicode blocks match to Telugu. That's why we are printing these, and we are getting all the tokens that have anything to do with Telugu from this Unicode block, and we realize that there are 233 tokens out of 256k tokens. So very little, but still from my experience, a well-trained token for each individual Unicode character beats any expansion that we do, unless we are training with billions and trillions of data where we might not have the compute for. Now let's do the same for Hindi. So similarly, Hindi, the script is unified in Devanagari. Basically, the script is for these major alphabets combined, which is Hindi, Sanskrit, Marathi, and again it falls from this Unicode block. This is basically A, I, I, U, Ru, La, A, etc. So again this Unicode block. Let's come, and again 9002 97F. So 9002 97F. This is what we are looking at. And we are iterating similarly through the Unicode character block and printing everything. So good, we have 1516 total Hindi, essentially Devanagari characters in our tokenizer of Gemma. That accounts to 0.6%, almost better than Telugu. Now again, let's look at an example, Unicode name for A. So what is this doing is essentially I'm taking this A and asking for the Unicode name, Devanagari letter A, just for examples, and I'm just again running it through and printing of a given word. So this is Raj, which means state. Let me just print it out. So as you can see, again Raj is comprised of 1 2 3 4 5 different Unicode code points from here. I think you call it a grapheme, which is a combination of Unicode code points. But at the end of the day, you can see the total number of tokens that represent a particular language in a tokenizer, as well as the percentage when compared to the total tokenizer. Similarly, let's now go ahead and explore Tamil Unicode block. Again, Tamil Unicode block is slightly smaller. Again, 80 to FF, B80 to BFF is the Tamil Unicode block. Let's run this. Awesome. Again, these are all the Tamil tokens, as you can see. 325 slightly better than 233 for Telugu. Again, slightly better than Telugu, 0.13 percentage, but less than Hindi. Of course, Hindi is almost 1500. Yeah, 1516 tokens in total. So here we have printed the exact token and token ID. So if you want, you can just go and look it up, the token ID here. Yeah, and just see that the token is actually present. We are not making it up in the tokenizer.json. Awesome. Now let me just again, for simplicity, print out the Unicode data name, Tamil letter I, which is the this one. Yeah, this one. Yeah, right here. So if you just do Unicode name, it will print out this one. Now let's go to Chinese characters. Basically, again, Chinese, just like Devanagari, it's an unified Unicode block that covers 20,992. I mean, the block is not shown here, but it's quite big, unlike Tamil, etc. For example, Tamil, let's see. Tamil, you have just 128 code points from this range to this range, just 128, but as opposed you have 20,992 code points. So let's take the whole code points again from 4E00 to 9FFF, and let's run the same thing for Chinese, Japanese, Korean. So this is a unified code block again that covers primarily languages Chinese, Japanese, and Korean. And again, you can see all of these. It has 23,839, so almost 10 percentage of the tokens in the 256k tokenizer come under this CJK block. So pretty good coverage. It might be very good if you fine tune on Chinese. And again, let's print the Unicode. Awesome. So CJK unified 649. I'm just printing some character of CJK block. So that's all for this video, and in the next video we will see how we can alter the tokenizer a little bit. Basically take the model, and in the output how we can, instead of doing generation and decoding between the 256k tokens, can we just slim the generation output to probably 3 or 4 tokens, positive, negative, neutral, and kind of do a sentiment analysis without any fine tuning, but just by stripping down the final layer of the decoded tokenizer. Let's see how we can do that in the next video. Thanks for watching.